Good morning and welcome to 220. Yeah, it has been sort of a rough or a weird several weeks. We're sort of behind, but we sort of we'll probably we'll try to record a makeup class. We'll schedule that so if those who want to attend can also attend live. But really, we also hope to get a bit more stuff on the homework side. So we'll post another couple of homeworks again just to get a feel for how we use the tools, uh, try to reinforce some of the stuff that we've been talking about in class. But ultimately, it actually gets less, at least in terms of the number of simulations and stuff like that. We sort of want to zero in on the design part. Right? As soon as you start designing stuff, we hopefully can, yeah, at least move along faster since we already have generated most of the curves that we probably will need. Okay, so hopefully everyone can hear me. It is sort of a very rainy morning. I'm actually trapped in somewhere in Tagaytay. But yeah, so all yeah, again, apologies for all that uh, class suspensions and stuff. Um, but yeah, hopefully we can cover a bunch of stuff today. And yes, the lecture will be recorded, and we'll post the recording on our website. Um, yeah, I think it's yeah the even yeah we'll try to make the face-to-face classes sort of recorded as well, but we'll see how that goes. But at least for the Zoom stuff, it's sort of straightforward. Okay. So today, I sort of really want just to round out our uh, transistor characteristics. And really, one of the things that we haven't really talked about is our frequency response. We'll get to we'll get to do a bunch of frequency response type uh the a bunch of frequency response simulations and homeworks and stuff like that together with the actual circuits. But yeah, so the one question is, yeah, sure. So yeah, no worries on the late homework. You can just submit them a bit late. That's fine. Uh, for this case, it's really just trying to understand the limitations, right? So when we talk about frequency response for transistors, we sort of want to talk about two things. One, what's our metric? Yeah. And really, okay, how does that limit, okay, the operation of our devices and ultimately our circuits, right? Um, and then hopefully we sort of can make that transition to our next topic, getting to electronic noise. And yeah, it's sort of a bit of a different simulation, and we'll set it up as well. Uh, and we'll try to get the homework for noise out as soon as possible as well. And the good news is that as soon as we get to noise and feedback, noise and all of that, then that sort of gets us in a very good position to start designing more sophisticated or more complex amplifiers. Right. Okay, so the first thing is really about this frequency response, but ultimately we know that frequency response is really going to be determined by your reactive elements. Uh, and obviously, in our transistors, it's mostly capacitances. Okay? If we had inductors, that would also limit the frequency response. But in the way we build our MOSFETs, right, that we build them out of PN junctions, it's really pretty much capacitances. So let us look at capacitances in our MOSFETs and let's try to understand where they're coming from, right? And ultimately, what are the characteristics, okay, of these capacitances and how can they limit operation, right? So let us take a typical NMOS. So if this is a typical NMOS device, right, then we sort of have a P substrate, right? And your uh, N regions, in general, you have your P tap, right? So this is going to be N plus, right? This is your gate, and potentially your source and drain. But remember, yeah, the reason why if you connect this to the body, right? Hopefully everyone remembers the reason why we have a P plus is to prevent the formation of Schottky diodes, right? So just to make sure, remember we had our Schottky diodes. Schottky diodes are metal semiconductor contacts. Okay? What happens if you have, let's say, a metal like aluminum, and I connect it directly to a P-type substrate? Then you will get a depletion region in the P-type, right? And what happens is if I look at my V versus I, it's going to look like a diode, right? This is going to look like this. But uh, in this particular instance, we don't want a Schottky diode. We want what we call an ohmic contact. Okay? That means I want it to look like a resistor rather than a diode. So one way is to significantly increase uh, the doping of your semiconductor, right? Because obviously a metal like aluminum has a lot of carriers, right? So that means it's really much very rich in electron, all metals. But if you start making this significantly highly doped, then the depletion region starts becoming less and less, right? So if the depletion region starts becoming less and less, then what really happens is, okay, instead of a diode characteristic, you start getting an ohmic contact, right? So that's why we sort of, every time you contact, let's say, a substrate, you always will see, something like a P plus type uh, region connected to the P because you don't want to get a diode there, right? You want to get something like a resistive contact. Okay, but that also presents certain problems because if you look at, okay, this thing, so any questions there? This would be quick review. If you start looking at this particular uh, setup, you see that, okay, what are the capacitances involved, right? So ultimately what we want to look at are what are the capacitances? And the capacitances are what we again call parasitic capacitances. Okay? They're parasitic capacitances because we don't really intend for them to exist, right? As much as possible, would have been nice if we can actually build transistors without capacitors. But because of the nature, right, of the way we construct MOSFETs, we have inherent capacitances. And you probably remember the largest capacitance you probably will see is our gate to source. So it's normally gate to source because we're assuming that you do have a channel in normal operation, right? You have a channel, and then you have this capacitance just because of, right, the very thin oxide layer, right? So we know that that capacitance is sort of approximately the capacitance from gate to source. And from the, from the structure, we know that it's a parallel plate capacitor, right? That's CGS. Yeah, that's a parallel plate capacitor. Or let's talk about this first, right? So not CGS, but let's talk about the oxide capacitance, that gate capacitance. Um, and that's really, eh, this one, right? So that I should have made this larger. It's the ox, right? So that thing again is going to be the permittivity times the area of the gate, right? So the width and length, and this is the permittivity of the oxide over the thickness of the oxide. Right? So it's a parallel plate capacitor, and it depends on obviously the area of the channel, the area of the gate. Uh, and the reason why it obviously dominates is because your oxide capacitance is going to be extremely thin. Right? This is going to be in the order of double-digit angstroms or something. Basically, several atomic layers thick, and that contributes a significant amount. Right? Okay, so that normally gives you the largest capacitance over there. But you do have a bunch of other things, right? So for example, one additional capacitance is your overlap capacitance because that gate is sort of, there's a small overlap to the source, and you also have that small overlap to the drain, right? And we call that our overlap capacitance. So this is the uh, overlap capacitance between gate and source. And you sort of have a gate to drain capacitance. Okay. This overlap, let's just call that CGD. Right. And for CGS, that is the sum of the overlap and COX. Right. That's a total this plus, yeah. So you do get a certain capacitance due to the overlap, but we'll see that, yeah, that's sort of relatively small, and that depends on the perimeter intersection between the source and the gate, and the gate and the drain. Right. So it's only dependent on, for example, the width of a transistor. Right. So if you look at this from 3D, or going into the screen, that's going to be the width of the transistor. Let's redraw. Right. So if this is your gate, right, and you have your source and drain, right, then it's only going to be dependent on the width. Right? That's the width, and that's how much overlap you can get. The capacitance between that gate and the drain, or the gate and the source. Right? So those are sort of the main capacitances that we see. However, yeah, if you look at this, there's still a bunch of other caps present. And one of them really is our the junction capacitances, right? So you know that this is an N going into a P, that's a PN junction, that gets you a junction capacitance, right? That's a capacitance from source to bulk. And this capacitance is a capacitance from drain to bulk. And that sort of looks like, okay, I have a capacitance from source to bulk and capacitance from, excuse me, drain to bulk. Okay. And if you remember, what's a characteristic of junction capacitances? Well, junction capacitances are present because of the depletion region. So the larger the reverse bias is, if I have a PN junction, I have a certain amount, a certain depletion region, and that's where really you store charge. So if you actually plot, if you remember, if you plot your voltage versus junction capacitance, right? So, you know, when you start increasing your voltage across a PN junction, what happens during forward bias, the depletion region becomes smaller and you actually have an increase in capacitance. However, if you have a reverse bias and the depletion region becomes larger, right, then the capacitance goes down, right? So it's sort of, again, for those who remember, it looks like that. Yeah, it's going to be exponential, some zero bias capacitance over there with zero bias, with zero voltage, you do have a depletion region, and that gives you uh you know some uh value for uh capacitance. And this sort of changes as a square or sometimes some factor. You get something like CJO over 1 plus V over the cut in voltage uh, squared or to some power close to 2. And that is equal to your junction cap. All right, so basically you do get this characteristic. So these are pretty much PN junctions, and they're nonlinear. Okay? All PN junction capacitances are nonlinear just because they're voltage dependent. While in most cases, COX is parallel plate. Okay? Uh, the overlaps are what we call fringe capacitances. Okay? They occur when, okay, if we have just a side view of the gate and let's say drain, right? Just because of that small overlap, because the when you build the N-type region, for example, it diffuses, right? So the original boundary sort of increases by a certain amount just because of diffusion. Then that sort of encroaches underneath the gate, right? So some of that encroaches underneath the gate, and that gives you some capacitance plus the fringe electric field going this way gets you our overlap capacitance over there, right? So that sort of gets you a good idea of at least the first order, what are the capacitances involved. But notice that even if this is parallel plate, we actually have seen this in the homework, right? That actually changes with voltage as well. Why? Because, right, the channel changes with voltage, right? You go from, if you have a gate voltage that is less than a threshold, you don't get an inversion layer. And then if you have, okay, so let's explain that, right? So let's just put it here. All right. So remember, if that's a gate, okay, uh, you do have several regions, right? So, for example, if this is your source and drain, just to illustrate, right? So if you don't have a channel, then the gate capacitance is this capacitance, right? Uh, going into the P substrate, right? But then, uh, what happens when you now have your if it's for example a very large negative voltage, your gate voltage, very large negative voltage, what happens is you have accumulation, right? You have accumulation of this N and this is P plus, right? So you get a lot more, and now you get this capacitance. But as soon as you deplete that, you have very little charge. And what happens is, okay, you actually get this capacitance and the capacitance of the P-type region, right? So you do get a certain amount of bulk capacitance over there. Um, then that sort of reduces, right, the capacitance because now you have a capacitance in series. Yeah, just because to make it clear, right? If I look at it from the bulk, or let's say that's where your ground is, right? I want to look at the capacitance there. Now, instead of just in accumulation, you get a lot of carriers over here. If this is P, you get P plus, right? Accumulation means, okay, I have a very large negative voltage. Yeah. So that acts like a parallel plate, and the only thing that you have is, okay, Cox. But if you don't have any accumulation, right, what you get is a series combination of the two caps, the oxide capacitance and the substrate capacitance. I mean, so just to make sure, why do you have a series? Because the permittivity of the oxide is different from the permittivity of silicon, right? So this oxide layer, and this is silicon. To get to the bulk, then you have two different permittivities, and that sort of looks like, okay, two capacitors in series. And if there are two capacitors in series, you expect that if I plot this, VGS versus the ox, in accumulation is relatively high, right? Just because it is just the ox. But as soon as you start increasing the voltage above zero, it actually goes down because you lose that channel, or you lose the accumulation layer, and it becomes a series cap. But what happens as soon as you get closer, for example, to the threshold voltage? Now you're forming an N channel. And now most of that cap is just going to be Cox, because if we assume that your source is also grounded, and that's pretty much most of your cap. Right. And then what happens is that sort of starts going up, right? Again, so you just have, okay, this is mainly your epsilon with length over Tox, Eox, and that's the same thing here. But then you actually drop when you lose either the accumulation layer or the actual inversion layer. Yeah. So that Cox is also going to be nonlinear, even though it is behaving like a parallel plate capacitor. Okay. And as you would imagine, if I have the bulk connected to ground and the source connected to ground, then this does not really play much of a role. But in most cases, we do have, maybe a lot of transistors that are not where the source is not connected to ground. For example, you have your cascode. So every time you have this, so this source, let's say, is connected to ground, but this source is not connected to ground. Right? So if it's not connected to ground, then you can feel the effects of that source to bulk capacitance. Especially if this is connected to ground, then this is connected to ground, the bulks are connected to ground. You will still get uh, some capacitance over there, right? So you'll feel the effects of that source to bulk just because the source is not going to be grounded. Okay. Okay, so any questions here? So what we're trying to look at is just, okay, you do have a bunch of capacitances, and we have, the mechanisms where they come from, right? So the oxide capacitance is really, approximately parallel plate. However, it's going to be a nonlinear cap because the bottom plate is changing, right? Either you have uh, no channel, you have accumulation, or you have an actual inversion channel, or anywhere in between. That affects the value of that oxide capacitance. Yeah. And then you do have the PN junction capacitance. So basically, anything with a PN junction will have a capacitor. Now it's going to be dependent on the depletion region of the PN junction, and it's going to be voltage dependent. Okay, okay, so these are sort of how we model capacitances uh, in an end. Any questions here? Questions? Okay. So if you don't have any questions, so we can look at what happens if you do have PMOS, for example. Well, for a PMOS, it's pretty much the same, except that you have an extra layer. For example, you have a well, right? And in most cases, the older devices, for example, if it's a PMOS, would have this type of well. So you still have an N or a P substrate. But to build your P transistors, I need an N well. Okay. So I can build a P plus here, P plus here. And again, we connect to the semiconductor with a highly doped region just to make sure we have ohmic contacts. Right? So you have your gate, you have your source, your drain, and this is your body connected to the well. You pretty much have exactly the same thing as your NMOS. You have your CGS, and we know that that's composed of your capacitance here and the overlap capacitance there. Yep. CGD will have this capacitance. And then you do have the PN junction capacitance, CSB, right? And CDB. However, again, this is a well, and it connects to P substrate. Then you do have uh, capacitance here. It's an N well capacitance to the substrate. And in most cases, if we're not using body biasing, for example, we don't really have, much to worry about that. However, in some cases, we actually want to control the body, right? Uh, and notice that, okay, this controlling this is not free, right? Because if I want to change the voltage dynamically on the body, I actually have to make sure that I can actually do that uh, in a reasonable amount of time. Then I need to be able to charge and discharge that NOL cap. But as you can see here, that is going to be dependent on the area contact area between the N well and the P substrate. And that encompasses the whole transistor. So in most cases, that capacitance is actually very large. Now, and this is, not only in PMOS transistors, but uh, in a lot of cases, you get, NMOS transistors as well. Right? Uh, so for example, in triple well processes, so you do have the uh, processes that are triple well. It means that, okay, even if I have a P substrate, I sort of still want to be able to isolate my N-type transistor so I can actually change the body bias for N-type, right? So notice that for this particular setup, I can change the body bias of a PMOS, but if they all share the same substrate, then when I change that body bias, I change it for all NMOS transistors. In a PMOS in a well, if I have one well for every PMOS, then I can actually change the body bias for a particular transistor. Now that's actually a very powerful thing. So people thought, why not build the process such that I can also change uh, the body bias of an NMOS, not for all NMOS, but for individual transistors. And then you get a triple well type thing where to get to triple well, so you have N wells and stuff like that for the PMOS, but to build triple well NMOS, you actually need two additional or you need one additional layer, and that's called a deep N well or a buried N well. Okay, so to be able to get isolated substrates for NMOS, in most cases, you actually need what we call a deep N well. A deep N well is an N well that you can bury underneath. Okay, it's normally an N well, a deep N well, and then you sort of that's the only real addition. Then after building a deep N well, you actually put in an N well. So that's an N well, and you build in an N well again. Okay? And this all works because of this what we call deep N well, or deep N well, or a buried N well. And if you can do this, then notice that what you get is an isolated P substrate. Right? So if you get an isolated P substrate like that, then it's sort of straightforward. Now I can build an NMOS transistor here, okay, with its own P plus that I can control, right? Its own body separate from uh, the other NMOS transistors. Um, the alternative is they also used to do what we call twin tub processes, where let's write that twin tub, where you do get uh, an N, and you actually also get a P layer that's separate, right? And then you can build NMOS transistors here, and you can build, PMOS transistors here. And yeah, just you need some isolation and stuff like that. But this is now a bit more popular, right? So most of the stuff that actually allows you to individually change body bias for NMOS are using triple weld just because, you just have one more process step. You just have to make sure you can build a deep end well. Um, yeah, but once you have that, then you sort of have additional capacitances between the body and the deep end well, and additional capacitance between the deep end well and the substrate, additional capacitance between the end well and the substrate, and so on, right? So you can imagine that as long as you have a p-n junction, you will have capacitances. Now the question is that capacitance going to be relevant to what you're doing or not? It depends on what's the voltage across the capacitor, right? So if the voltage across the capacitor is always zero, then it's probably not going to matter. Or if the voltage across the capacitor is static, like it's always DC, it does not change, then it's probably not going to matter. However, what matters is if you have capacitors, right, with time varying voltages, then that requires time varying currents. Right? Then that could affect the performance, frequency performance, or the time domain performance of your circuit. Okay, okay, so any questions here? All right, questions. So we sort of can imagine that, yeah, okay, we'll have a bunch of capacitors associated with every transistors. Uh, and we hopefully can understand where they're coming from, right? What type of capacitances those things are. And it gives us an idea, right? So, okay, which of these things change with which voltage? And as you probably would imagine, the p-n junction capacitances, they actually also change with temperature, right? Because they're semiconductors, then these capacitances also change with temperature, less so on the parallel plate, right? So for the parallel plate, they're sort of less susceptible to temperature change, uh, just because the oxide, distance does not really change with temperature, as opposed to junction capacitances where the depletion region changes with temperature. Yeah. Okay, good. So any questions here? Oh, by the way, for triple well, it's also very important to be able to bias this, right? So again, you put an N plus, and then you sort of need to bias the well. Uh, because again, in normal operation, you don't want any of these junctions to be forward bias, right? So you make sure you bias everything in a reverse bias manner, just because again, these things are not meant to be devices; they're meant for isolation. Okay? And if they're meant for isolation, then you sort of want to make sure that they're all reverse bias, so you don't have much of a current flowing. Right? Again, you will have leakage currents and so on and so forth, but in most cases, those are orders of magnitude smaller than your actual current. And at the same time, if you maintain very little voltage, then the actual leakage power is small. Okay, okay, good. So any questions here? Yeah. So that means every time we build transistors, uh, it's nice to also understand, how much these capacitors are affecting us. And it also pays to be able to run simulations sort of accurately, right? When we say accurately, okay, I want a good estimate on the capacitances, right? So how do we actually get a lot of these capacitance values into, for example, SPICE? Uh, we actually have explicit instructions, especially if you look at the homework that we have when we build transistors. Okay, we normally put in these parameters. Okay? So we have, for example, the area. So AS means area of the source. Okay. AD means area of the drain. But we also know that, okay, you have PS, that's the perimeter of the source, and perimeter of the drain. So what does this mean? I want to be able to, aside from, right? So when we calculate capacitances, this is going to be known, right? So you always know the width and length of your transistor, right? So this is the width, this is the length. I can actually calculate how much CGS or Cox I have, right? What I don't have is what are the capacitance, right? For example, the fringe capacitance over here, or the overlap capacitance, and the capacitance uh, to the substrate. Now, top view, this is sort of good, but if you look at this capacitance to the substrate also includes what we call sidewall capacitances. Yeah. The capacitance on the edges, it's sort of the same, right? It's the same PN junction. Um, but given the layout, it actually is a bit different, right? So we're given the area of the source, and that just means, okay, what is this area? Okay. Uh, and if you're just given the width and length, this sort of is unknown, right? Because you actually need to figure out what is that dimension, right? So, how far does the source extend from the gate? Um, and that is sort of, if in this example, if I have like a micron, then the area of the source is something like that 1 micron times the width. Right? And that allows me to calculate what this area is, right? The bottom part of the source, and it allows me to say, okay, this is my uh capacitance over there, right? Because that's the area of the PN junction. However, like we said, there's going to be some capacitance on the side, and that's what your perimeter is going to be. Now, notice what's the perimeter of this. It's a perimeter uh here, right? Because that also has some capacitance to the substrate, and it's going to be this side, and it's going to be this side, right? So all three sides will be your perimeter of the source. And that's why it's this 1 micron, this 1 micron plus the width, right? So it's 2 microns plus the width. And that allows you to calculate uh, this capacitance, right? So actually, it allows SPICE to calculate this capacitance. So if you write out your SPICE model, you'll see that we always, to have a realistic transistor, we have to specify the area of the source and the area of the drain, right? We also uh, notice that, you know, again, make sure the perimeter does not include the side next to the gate because because we don't really calculate this capacitance because that's going to be part of the channel. Okay? Because you might notice that that's how we sort of write out our SPICE model. When we instantiate transistors, we actually put it there. Now, the problem is, it depends on your simulator. Some simulators, some SPICE versions, if you don't put the source and drain, right, they'll actually just put in 0. And if you put in 0, that's not a very good simulation, right? Because, okay, you run a simulation, you run frequency response, and you get very good numbers just because you did not consider any of the junction capacitances, right? So it's very important. Every time we run simulations, we have to add a lot of these information. Now that sort of uh, still requires uh, you know some, let's say, advanced knowledge of how you will lay out your transistor. And why is that? Just because, as you can see on the figure below, right? It's really going to be uh, layout dependent. So if you do have a wide uh, transistor, then as you probably imagine, it's better to put in multiple fingers instead of one very wide transistor. Um, for one, you reduce the resistance that you need on the gate, right? So versus the resistance that you see on that gate, right? So you break it up, then okay, I have less resistance, and the signal will travel half the distance, right? So you actually improve this by quite a bit. At the same time, notice that the capacitance here will have very little uh, perimeter, right? It's going to be the perimeter of this drain is just going to be 2 micron, right? Because you sort of hid the perimeter there. And at the same time, if you look at the total cap, you're going to be sharing this region, right? So you actually have approximately, you know, a reduction in uh, the capacitance that you have. And I think you can see here with this calculation, you can see here the total cap, this is symmetric, right? So that means the total cap from the source to bulk and drain to bulk is 28. Um, but for here, you can see that the source actually increases by a small amount. Why? Because you have that extra perimeter, right, here and here. Instead of just having one whole thing, right, you have that extra perimeter. But notice that the drain to bulk is significantly smaller. Yeah. Just because you actually don't count the two perimeters here because they're connected next to the gate, the channel region of a transistor. So the only thing that you're looking at is uh, this and this, right? So you get to when you get to share those regions, then you amortize that over the two transistors, and at the same time, you actually don't have a large width exposed to the substrate, right? So you get rid of that as well. So you can play games here. Say, okay, I can live with a higher source to bulk, but I want to reduce my drain to bulk. Okay, and why would you want to reduce, for example, the drain to bulk, right? Again, if that is connected to your output, right? So that is connected to your, let's say you have an amplifier and that's connected to your output, right? And it's driving a cap, then you sort of, okay, if this is already a very large cap or you want very high frequencies, and I sort of don't want any other things connected to that output, maybe I want to minimize that particular output, right? Or that particular output capacitance. Now, notice that this also gives us a certain amount of drain to bulk or drain to gate, right? Or gate to drain. For example, this one, notice that it's still going to be the same, but one issue that we sort of want to make is that that gate to drain, it sort of appears here, right? If this is your source, this is your gate and drain. So that CGD appears there. And it turns out, even though it's relatively small, as we saw, right? So over here, right? So that capacitance is just an overlap capacitance, right? That's relatively small compared to everything else. But the problem is, okay, why do we care? Because that CGD actually can look like a very large capacitor. And this is called, sometimes called a Miller capacitance. Okay? And why is it called a Miller capacitance? Because this is very important, right? And in most cases, this actually starts to limit the maximum bandwidth or the maximum frequency that we can achieve in our transistors. That's because if you remember, if I have an inverting amplifier, so something like minus A, what happens if I actually put in a capacitor, right, between the input and output of my amplifier? Right? So if I put in a capacitor, the input and output, the question is, okay, how much current do I need to drive this particular amplifier? Well, if you notice that, okay, uh, if I look at this, what's the voltage across the cap? Okay, and if I look at the voltage across the cap, then if this is in, V in, this is V out, but V out is negative A times V in, right? It's an inverting cap. So the voltage across the cap is V in minus V out. And that's actually V in plus A V in, right? And it's V in times 1 plus A, and that's the voltage across the cap, right? And what does that mean? If I want to take the current, then I just take the current, okay, is C dVC over dt, right? But dVC is just C times 1 plus A times dV in over dt. So every time you have a capacitance across an inverting amplifier, when obviously a common source amplifier is an inverting amplifier, what happens, right? It looks like that the current I need is actually the same current I need to charge a capacitance of the input with value C times 1 plus A, right? Because this looks like the actual capacitance you're charging. So even though you have a very small capacitance over here, but if you put it across an amplifier, an inverting amplifier with relatively large gain, from the input, it actually looks like the input is charging a very large capacitance, right? So even if, for example, you have 1 femtofarad or sub femtofarad for this capacitor, right? But if I put it across an amplifier with a gain of 1 million, right, or 100,000 or a gain of 10,000, then it looks like from the input's point of view, I'm charging a very large capacitor, and that means I need a very large current, right? And if I cannot provide that current, then it takes a longer time to charge and discharge that capacitor. So this is known as Miller effect. Okay? It's known as the Miller effect. Okay? And that's why that capacitor is sometimes known as the Miller capacitor. So we'll see later on as we build amplifiers, even though that overlap cap is small, when you start building amplifiers with higher and higher gain, or if you're actually starting to push very high frequencies, even that overlap cap starts to limit uh, the performance, right? So what really happens is, okay, maybe I'll trade off, back off on the gain, right? So that I can reach a certain bandwidth. So that's really, yeah, something that it's sometimes very, very easy to miss. Just because, okay, if you list the capacitances, yeah, Spice can allow you to do that, right? List all the capacitances and then rank them from largest to smallest. And then you start trying to figure out, what are the largest caps and why your circuit is not, uh, you know, running at the speed that you want. It might be easy to miss, right? Because Miller caps are very small, CGDs are very small. So it's probably going to be at the bottom of the list. But then when you start running in actual operation, they can dominate, right? So it's very important to understand, okay, where all of these caps are coming from and which could be significant for your application, right? So it's always dependent on what you want to do. Again, if this were a non-inverting amplifier, then that's fine, right? So if this were a non-inverting amplifier with gain A, then you sort of still will have this issue, but it's going to be 1 minus A, right? And it's going to be, okay, actually going to be a smaller cap, right? But what you sort of really want to understand is, yeah, when you put stuff in feedback, a lot of things change, right? Okay, good. So any questions here? And so hopefully we've heard of the Miller effect before. And this is the reason why when we talk about feedback and we talk about Miller compensation, eh, eh, it's a different thing, right? But it uses the same effect. Miller compensation is, okay, I have an amplifier and I would actually want to add a pole. For example, if I have a two-stage amplifier, eh, I want to add a pole here. So the option is, okay, if I want to add a pole to make my circuit a bit more stable, right? One option is I'll put in a very large capacitor there. But we know that capacitors sort of take up a lot of area, right? And in most cases, I build the inverting amplifiers. So Miller compensation just says, yeah, I'll take advantage of the Miller effect. And instead of building a cap there, I can actually put the cap here and be 8 times smaller than the cap over here, right? Or 1 plus 8 times smaller, right? So instead of putting the cap here to build my pole, could be a low frequency pole, so I need a lot of cap, right? I can just use Miller and say, okay, it's actually easier, or at least it consumes less area if I put it here for the same effect, right? From the input point of view, I see a large pole, but I don't have to build a very large cap. I can build a smaller cap. And then you can start doing optimizations and stuff like that. But yeah, so that's you can also use that Miller effect to do compensation in your feedback amplifiers, and you can play games with that, right? So a lot of these effects, it's very important to understand that, yeah, this is a bad effect, or I can actually use this to optimize, right? So a lot of these things are none of them are inherently bad, uh, and people have found different uses for different effects, right? So someone's very bad effect can actually be someone's very good effect. Yeah. Okay, good. So any questions here? Yeah. Okay, so how do we now measure the effect of these capacitances uh, in the performance of our transistors? Well, as you've seen in the homework, one very important metric is our FT, or our transition frequency. Okay? And by definition, this is the frequency where your current gain is equal to 1. And what does that current gain mean? It means that, okay, in small signal, I have this thing. Oh, so let me clarify. This is the short circuit current gain. Uh, that means in small signal, I want to put in some small signal current, right? And is short circuit, then that means in small signal, this is connecting ground. I want to check, okay, if this is I in and this is I out, okay, at what frequency will those two be equal? Right, and that means I don't have any current gain anymore, and that's probably the maximum usable frequency of my transistor. Okay, so first of all, this is in small signal. Okay? So in small signal, yeah, you might say, okay, what does a short look like? So remember, in the way we build small signal, right? So okay, I have a transistor, uh, and then I put in, so let's say this way. Yeah. I have a transistor, and I want to put in a small signal short. The small signal short just means that, okay, it's actually some constant uh, DC voltage, right? If it's a constant DC voltage in a small signal, it looks like a short. Again, make sure we understand, right? So when we say small signal, right, let's say it this way, right? In small signal, the output characteristic, VDS versus ID, okay, looks something like this. In small signal, what we really want is, okay, uh, if I change this by a small amount, okay, how much will this change? Okay, so if I want a small signal short, uh, what does that mean? It means that in a small signal short, the change in voltage, right, is equal to the small signal. That means this change, delta V and delta I. But what's a short? A short means the voltage is always zero, right, for any current. And that means a short actually looks like, if I have VI, right, a small signal short sort of looks like this, right? It has delta V, 0 delta V for any delta I. Right? So this is the characteristic of a constant voltage source. Okay? For a constant voltage source, I cannot change the voltage. So delta V is always 0, right? So there's always going to be 0 small signal voltage here. And again, if you have 0 volts and any current, that looks like a short in small signal, right? So that means, okay, if I want to do uh, uh, short circuit current gain in large signal, I just have to put in a constant voltage source, right? And then I sort of bias this thing. You see that in the homework. Uh, you have to bias, so to put that transistor in some region of operation. Okay? So what we do is, okay, we put in some VGS, and then that gives me, okay, some DC drain current, right? So this is my bias. Now, once I bias this transistor, it has a certain small signal model. Right? The small signal model is, okay, I have CGS, uh, then GM VGS, okay, and R out. and then CGD. It's a gate, source, and drain. So just to be clear, right, this is what you need to get this small signal, right? I need a VGS and I need a VDS. It gives me an ID. So once I have all those, I can actually start to calculate this GM, this R out, and I can estimate what CGS is and what CGD is. CGD is going to be mainly from the overlap. I can use this drain current to figure out the actual value of CGS, right? It gives me an idea of, okay, how far into saturation, this is how much channel. And if I figure out how much channel, then I can figure out how much capacitance I have over here. Oops. Let's make that a bit more clear. I can have this. So if I know how much channel I have, then I can figure out how much cap I have over there, which is CGS. So once you get this, the question is, so this is what we call your DC bias. This is your quiescent point. Uh, this is where this transistor is sitting at in DC. Now, transmission frequency is a small signal parameter. That means I want to inject some small signal input current. Okay? Now, this is a bit tricky, and you see this in the homework. It's actually nice to be able to just inject a small signal current here, which is what you probably would do. Yeah. Small signal current, and I want to measure the small signal current over here, right? A drain current, and let's say this is a gate current. However, in small signal, okay, uh, the current flows into the lower impedance, right? But notice that this is a VGS. This is also a DC source. And a DC source, again, just like VDS here, it looks like a short in small signal. So if you don't do anything, all your small signal current will actually just flow into the source, into the VGS voltage source, and none of that will flow into your transistor. Right. But what we want is still you want to maintain the DC voltage over here while you're putting in uh, your small signal current. Right? So in your homework, you'll see that one way we can get around that is put in a very large inductor. Right? So what's nice about this inductor? So we normally just call that L infinity, ideally, right? And why is that? Because an inductor in DC is a short. That means in DC, I can actually provide the VGS to the transistor. But what happens when I start increasing the frequency? When I start increasing the frequency, the impedance here is j omega L, or the impedance increases with omega. So as soon as I start increasing that frequency, the impedance of that inductor starts increasing, right? And that gives me what I want. That means, okay, all that current should go into the transistor instead of back into the voltage source. So to be able to get a larger range of frequencies, then I want to increase that L. Ideally, I want that impedance, j omega L, to be infinite at any frequency greater than 0, right? So that just means, okay, I can just increase this so that at the frequency that I want, that pretty much looks like an open circuit. So all your small signal goes into that transistor. Yeah. I hope that that's sort of clear. That's the reason why we sort of had that particular circuit. But that's one way of doing that. Yeah. And if you do that, then okay, I can actually look at my model and say, okay, that looks like me putting in some small signal input current. Yeah. And then again, this is going to be connected to a voltage source, then that means a drain from the small signal point of view is shorted, right? So hopefully we understand, right? So a short in small signal just means either, uh, a constant voltage source in large signal, right? Or a short, doesn't matter, right? So it's the same thing. The short is a short, a voltage source, a DC voltage source is a short in small signal. And now we can actually start calculating, okay, I want to figure out what this current is, right? The drain current or the output. And I want it such that the current gain is 1. So very quickly, say, well, what is that drain current in small signal? Well, since this is a short, let's say this is ground, and this is a short, uh, there's no current flowing through the output impedance, right? Because there's no voltage, there's no small signal voltage across RO, right? So all of this current is approximately GM times VGS, right? Approximately all of that, okay? So now what's VGS? If this is VGS, and notice that since this is a short, okay, this is also VGS. Hopefully that's clear because this gate and this is source, and this is all shorted out, and this is also uh you know the source, right? Because the drain is shorted to the source in small signal, again in small signal, right? In large signal, it looks like a voltage source like this. In small signal, it's connected to the source. Yeah. And that sort of just is easy right now because VGS is just equal to the gate current times the impedance of that cap. Okay? Where the impedance of the cap, so hopefully this is also clear since this have the same voltage, and CGS is actually in parallel with TGD. Right? So I times the impedance of the cap is 1 over j omega CGS plus CGD. Yeah. Okay, then I can actually just plug that in here. ID is equal to GM times IG over j omega CGS plus CGD. Okay. And let's put a different color. As you'd see, ID over IG is equal to GM over j omega CGS plus CGD. Okay. So if I take the magnitude of this, okay, take the magnitude of that and equate that to 1, okay, then that means that frequency here is my transition frequency omega t. Right? So in the magnitude, then the magnitude of j is just 1, right? So what you get is, okay, what is omega t? Omega t now, I just move this over here, then omega t is just gm over cgs plus cgd. Okay? And that's what we have in the homework. So make sure we understand, right? So this is the small signal short circuit current gain. That means above this, I don't have any current gain anymore. And it's probably not going to be a usable transistor. I mean, I can't build an amplifier out of that because you can't get enough gain. But in general, we don't really go close to omega t. Or just make sure, right? Ft is so omega t is 2 pi ft, right? The same thing. So this is in hertz. This is in radians per second. Okay, so what we sort of normally do is we once we get omega t, we sort of want to operate maybe 1 to 3 decades below omega t. That means if your omega t is something like a gigahertz, okay, you probably want to use that, something like 100 megahertz or less. Why? Because again, as if imagine this, it's going to be something like a low pass thing, like 1 over omega, or not even that, right? It looks like something like this. Okay, so when you get a gain of 1, that's omega t. But then you sort of don't want a gain of 1, right? You sort of want to back off a few decades, so you do have a significant amount of current gain, right? Okay, so any questions there? Right? So transition frequency is a very good metric to figure out the usable frequency range of your transistor. Now, the other thing is, as you would imagine, since GM, right, is dependent on your DC bias, right, what that ID is going to be, and then by changing ID, you change GM. And you change GM, you change your transition frequency. So omega t is actually a characteristic of your transistor, but not only a transistor, but of the DC bias of your transistor. So when you start looking at, okay, designing with, a bunch of specs involved, and then, okay, what GM do I use? It's the GM that you need to drive your capacitance, for example. But then with that GM, you have to check, are you actually, you know, still operating below the FT of your transistor? And the second thing is that notice that your FT is dependent on CGS and CGD. So the amount of parasitics involved, the amount of parasitics in your transistor determines how fast your transistor can operate. So then that also plays with, okay, how will I lay out this transistor to reduce these parasitics to get this particular frequency, or to try and meet this particular bandwidth requirement or whatever. Okay. Okay, good. So any questions here? Now, hopefully this is clear. We sort of just looked at small signal and then looked at one very important metric for a single transistor. Right? Obviously, when we start building circuits, we have other metrics like bandwidth or gain bandwidth products or whatever. But it's very important. Okay, for each individual transistor, we sort of use them in their particular usable frequency range, and we'll see how biasing affects that, right? And how layout should affect that. Okay, so very quickly before the break, we can see that uh, one of the reasons why we actually like to reduce the length of your transistor is because your transition frequency increases significantly. Right? Uh, and we know that, so this is sort of very important, right? So GM, we know that that's going to be approximately a function of 1 over L. Right? So the smaller the length, the more current. And in square law, this is proportional to width over length. Okay? But at the same time, your CGS is proportional to the length, right? And that means, okay, it's proportional to the area, right? So width and length, and this is proportional to width over length. And as you can see, what you want to optimize is GM over CGS. And that's FT approximately if you ignore CGD. And that is going to be proportional to 1 over L squared. Right? So this is the critical thing. The reason why you want a lot of air, to continue reducing your length is because you get significantly uh, significant improvements in your FT, right? Because now approximately FT is going to be proportional to 1 over L squared. And as you can see here, you sort of can start increasing that to get higher and higher FTs. But notice again here, and you'll see this in your homework, once you change the bias, and that just means I'm changing my drain current, I can go for this particular technology, I can go from here all the way up to here, right? And this is the reason, okay, if I bias it here, then I'm actually in, for example, subthreshold. Okay? Where if I bias it here, then I'm in super threshold. No. And as you would imagine, the GM here is small, while the GM here is large. GM is small. Okay. This also brings up a very interesting situation for us. Remember, we plotted, and this is again the homework, we plotted two things. We plotted GM over ID, right? Our power efficiency, right? And we say, okay, efficiency peaks over here when it looks like a bipolar, and efficiency drops, right? Uh, as you increase VGS. But then the opposite thing occurs for FT. Speed goes up as you increase VGS. So energy efficiency goes down, speed goes up, or the opposite, right? Energy efficiency goes up and speed goes down. So inherently, you already see the power versus speed trade-off, even in the device itself, right? If I want a faster device, I actually will spend a lot more power. If I can back off in terms of speed, I can actually save power. Yeah. And one of the reasons to remember, we talked about this earlier, and this is nice because I can come up with a composite figure of merit. I just multiply FT with GM over ID, and okay, I get a good estimate of, you know, let's say I don't really have a good spec or at least a generic amplifier, and I want to have a good trade-off between power and speed. Then maybe I can just initially use this and assign, okay, this sort of peaks at something like, 100, millivolts of V star, and that's fine. So that's normally where we, uh, especially in our previous design example, said, okay, 200 millivolts is normally a good initial guess, right? Just because that gives me approximately, somewhere here, it's a good trade-off between efficiency and speed. And having said that, now if I sort of want more power efficiency, I can just move this way, right? Or left. If I want more power efficiency, I can change my bias and move this way for a bit. Or if I see that, yeah, I might need more bandwidth, my bandwidth is too small, the performance at speed is actually slow, then I can move the bias point a bit closer to the right and get a higher FT per transistor. Right now, it's sort of going to depend on the application, but it's really important to understand, right? Okay, every time, given a transistor, right, every time I want to increase the speed, there is a corresponding power penalty for that. Okay, and hopefully this is something that you've already seen in the homework, and you see that for our process, it's somewhere around, right? So a little less than 200 millivolts, just like this one. Uh, and it's several, yeah, 100 gigahertz or so. But yeah, so it's really a key. Okay, if I want to use V star, not only do I want to look at energy efficiency, but it has to be coupled with, okay, this is going to affect uh, the bandwidth or the speed of this particular transistor, and obviously that affects the bandwidth and speed of whatever circuit you're building. Okay. So that's a good rule of thumb, at least our initial guide for, okay, what how do I bias this transistor? Depends on how much power efficiency I need versus how much speed I need versus how much GM I need. Right. So, and we will develop those things a bit more as we go along. Okay. Okay, good. So any questions here? Questions? Okay. Yeah, so this is actually a good time to take a break. So we will stop here for a bit and we'll take a 15-minute break. So we'll get back here at 8:52, okay? Uh, or 8:52, 8:47. No, my brain is not working, right? So it is 8:52. So let's go back here at 8:52 and let's start a new topic, right? We'll start on noise, and let us see how far we can get with the noise. Okay, good. So let's stop here and let's resume in 15 minutes. Okay, let's get started. Yeah, so like I said, we sort of want to shift gears a bit, and yeah, after trying to understand transistors, at least from our traditional level, okay, what are the voltages, current, frequency response, and maybe a few metrics about how we think about power efficiency and how that goes into the design process and how to handle, you know, uh, devices that really do not follow the square law. We sort of, yeah, should have a good idea of how we can do that and how we can be very productive and efficient in terms of design. One of the things that we sort of also, uh, want to look at are other characteristics of our transistors that actually significantly affect the performance of our devices, especially for high precision devices like A to D converters, filters, anything that requires, uh, you know, processing very small signals like receivers for wireless, cellular, for example, have ridiculously low input levels, 100 minus 100 dBm or whatever. And then you do try to figure out, okay, what limits our ability to do that, right? So for example, if I'm sensing vibration from piezoelectric devices or from MEMS devices that are in the microvolt range, um, it turns out that one of the main limitations and one that we spend a lot of power on is is noise. So that's what we're going to talk about uh, today. And just make sure, right? So we are, yes, noise sort of uh, is one of those terms that have been used around for so many things, and it could mean anything, right? It could mean a lot of things. One interpretation of noise is what we call interference noise. Okay? It's the noise that uh, gets coupled into your circuit from your surroundings, like power supply noise, 60 hertz noise, and so on and so forth. Uh, and they're from the environment. But in most cases, uh, these type of noise are deterministic. Okay? Meaning, I know something about the noise, right? It could be power line, like 60 hertz. Okay? And if I know something about the noise, I know the shape, I know the frequency, it's a sinusoid and whatever, then this actually is easy to cancel. Okay? Just like your noise cancellation headsets, right? Because the noise can actually be measured. Uh, the easy thing is, okay, I'll just look at what signal is interfering, and then I generate 180 degrees version of that signal, and then as I add it, right? So I just cancel it out completely. And this is not what we want to actually look at in the course. What we want to look at, and this is where you sort of, as a designer, you spend a lot of time, is inherent noise. Okay? And this is the noise generated by our devices or devices in general. Right? So this is the more uh, you know sophisticated or involved noise, or more complex, or harder to remove noise because this is generated by the circuits themselves, right? So if you build a transistor circuit, if you build an amplifier out of those transistors themselves are generating noise. Uh, And as a result, this limits how much, how small of a signal you can process, right? And since we will talk about this in detail, but one characteristic of this noise, inherent device noise, is that it is random. Okay? And again, what do we mean by random? Basically, you cannot predict. The actual voltage or current or whatever that comes next. So even if I measure the noise at this point in time, I will not be able to 100% predict what that next noise value would be. Okay? But the good news is that even though we cannot predict the instantaneous values of noise, uh, we can predict or we can, let's say, characterize noise, right? And the good news is that you know, we do have ways to handle random, right? And that's the whole point of your statistics and probabilities class, how to handle random things. And it's not really trying to look at individual voltages and currents at a certain point in time. We're looking at, okay, what happens if we aggregate all of this? What happens on the average, right? What happens, can I look at these random values, these random variables, and say, okay, are there any distinguishing characteristics? And can I sort of look at different classes of things, right? So in most cases, you cannot really predict, but we can look at what we call statistics. Right? What are the statistics of these random phenomenon? And then maybe we can look at, as you probably would imagine, the easiest thing like the mean, the variances. But more importantly, we sort of can start looking at limits. Okay. That means, okay, how much is this random phenomenon or random variable changing? And if it's a Gaussian, so that's the idea for the whole statistics and probability field, right? So I'll have a mean and I'll have some sort of variance that gets me, uh, if it's varying by a lot or varying by relatively narrow amount. So I'll have another sigma squared prime or sigma 1, sigma 2, where I can now characterize, okay, if I have a larger variance, then the numbers or the values that I get are more spread out. It's still random. I cannot predict what will happen next. But on the average, I see that they're clustered around certain points. Okay? And then I can start looking at, okay, limits, right? So that means, okay, what is, at some point, if I model this a Gaussian, then, after 3 sigma, I know that there's going to be a very low probability of that happening. It's not impossible, right? So again, that's the thing. Right? It's not impossible for that thing not to happen, but the probability is low. Right? And then we define that whole idea of, okay, a whole branch of mathematics that deals with all of these random things. And that's good because that allows us to uh, really gives us a framework to work with all of these random things. Yeah. Okay, so as you would imagine, we probably have seen a lot of these things before, right? So again, if you have even for a resistor, eh, for a resistor, it's just a simple resistor, but if you put in an oscilloscope and measure the terminals and try to look at the voltage across the resistor, you're not going to get something like 0 volt, right? If you zoom in far enough, you get something like this. Right? And you probably would ask, okay, is that actually an error or is that actually happening? It turns out that that's actually happening and you can measure that. Right? It's random, but you can actually measure noise. So if you go into the oscilloscope and look at that, and just by a resistor with nothing connected to the resistor except that particular oscilloscope, then you get something like this. So why do we get something like this? It turns out, remember, your electrons, right? If you have an electron, that electron is not actually just standing still, right? Even if it's just inside, let's say, a resistor with no voltage, remember, an electron actually starts moving, but it moves in random directions, right? And that movement is known as the instantaneous velocity. Okay? And that depends on what? It turns out it depends on thermal energy. Okay? How much thermal energy your electrons have is how fast they're actually moving, but they're moving randomly. So the average velocity, or what they call the group velocity, is just 0, right? So on the average, the electron still stays there, right? That's the sort of mean. But instantaneously, it actually moves around. Okay? So if you have a lot of these electrons in your resistor, then if you measure the voltage, those electrons moving through the material sort of can generate a voltage, right? Current going through generates your voltage, falling down a potential. Then it sort of say, okay, I get this random pattern of output voltage. Right? And this is true even if you apply a voltage or an electric field, right? So when you apply an electric field, your electron is still moving randomly, but now it's moving at sort of, you know, in the direction of the electric field, it's sort of moving at an average velocity or, you know, some group velocity uh, in the opposite direction of the electric field. Right? So if the electric field is, for example, in this way, uh, then it sort of gets you this movement. But still, on top of that, you get uh, this random motion. Right? Now, if it's thermal energy, then you would expect that if I increase the temperature, I actually will increase the noise. Right? And it turns out that that's actually the case for resistors. Okay, so for resistors, right, what we get is increasing your temperature increases thermal energy and increases, okay, the velocity and pretty much the distance this electron moves. And we can measure that. And since it's dependent on temperature, this is known as thermal noise. Okay? Thermal noise is due to the random movement of electrons. And one of the things that we sort of will see later on is that can we control this? Right? Can we sort of limit how large this is? And what are the properties of this particular noise? But just off the bat, right, as you can see, if your signal that you want if the signal that I want is less than the signal, the noise signal generated by your own amplifiers, then you're not sure if at the output if you're actually amplifying your input signal or you're just generating or outputting the noise of your own amplifier. Right? And hence, it's very important that we sort of understand our main metric for this is our signal to noise ratio. Right? So that means, okay, I want to figure out how large this noise is relative to the signal that I want to process. But to be able to do that, then we sort of need to figure out a bit more about this whole noise thing, right? So let's start with the resistor, and then let's go through our devices like diodes and transistors, and we'll make the case that, you know, ideal inductors and capacitors should not generate noise. And we'll talk about that. Right. Okay, so let's talk about uh, resistor thermal noise. Okay. Now, uh, resistor thermal noise. One of the things, the foundations for our noise analysis uh, is really pretty much due to the work by Boltzmann. So you know that, okay, Boltzmann says, okay, what is the thermal energy that is available? Okay, what does that even mean? What is the thermal energy available in, let's say, a particular system or circuit that we see? Right? And Boltzmann said, yeah, it is equal to Kp. That means if I had a resistor, oops, let's talk about this, right? So if I have a resistor and I call it a noisy resistor, it's a resistor that generates thermal noise. How much energy will that generate? Boltzmann says it's equal to Kp. Uh, so if we think about this, how do we model noisy resistors? Well, we can model our noise as our noise generators. Hmm? So for example, I'll model this noisy resistor as some noiseless resistor. This is now noiseless with, let's say, a thermal voltage noise generator. So to differentiate uh, the voltages for noise and normal voltages, we sort of use this, right? So this just means it's a noise generator, and we'll see that the way we write out uh, noise generators is it is it has weird symbols, but we'll talk about that, right? So oops, what's going on? Okay. So we can tell, okay, let's say that we have a voltage noise generator, Vn. Uh, but remember, we cannot really uh, you know, predict the value of the voltage instantaneously, right? So in most cases, it does not make sense to talk about Vn. What we normally talk about is noise power. Okay? That's like your signal to noise ratio. That's a signal power to noise power ratio. So the way we write this out is not the voltage of the noise, but the mean square of the voltage of the noise. Right? And we'll talk about this in a bit, right? But ultimately, what you want is, okay, I want noise power. So I'll take each noise component, square that, and take the mean, right? So it's the mean square of the noise. And in statistics or in probability, if you take the mean of the square, that's actually what? That's actually the variance, okay? Sigma squared, right? So if you take the mean square, that's the variance, or the expectation of the square of the random variable, right? But yeah, so we're talking about variance, and that actually gives us power, right? It's now voltage or current squared, and that gives you the mean square or the noise power. Voltage noise or current noise, the same, right? So you get V squared or I squared. But we sort of write it out this way, right? And we'll expound on this in a bit. But one way we can actually start working with noisy devices is, how do you model those noisy devices? Well, for resistors, it's relatively straightforward. I'll just model it this way, right? I'll model it as uh, a noiseless resistor with some noise generator. So now the question is, what is that? What's the value of this noise generator? Then we go back to uh, Boltzmann, said, okay, the energy you get is pretty much going to be kT. So that means this is the maximum energy you get. So if I want to get the maximum power out of this noisy resistor, then the only way I can do that, hopefully this is clear, is, okay, if I have this noisy resistor R, I make it noiseless, and then I have a noise generator, Vn squared. Okay. And how do I get the most power out of that? Well, I actually put in a resistor of the same value, right? I get maximum power transfer. So what's going to be the voltage, or what's the power I can transfer to the resistor R? So if I have, okay, so just for circuit analysis, let's say this is Vn. If I have, the same resistor, this is going to be Vn over 2, right? And the power I deliver to the resistor is going to be what? This squared, Vn squared over 4, right? Times R, or V over R, sorry. V over R times 1 over R, right? Uh, and Boltzmann says the energy is going to be equal to kT. But that's energy. So what's the relationship between energy and power? It's power is energy per unit time. So you sort of want to, divide this over time, or we'll see that, okay, if I sort of have, and we'll talk about this, right? If I think of this as a spectrum, then I want to get the components over the whole spectrum, right? And then, so this would be multiplied by the bandwidth of whatever I'm using to measure. Okay. So this is energy. Okay. And this is your bandwidth. And the bandwidth of your measuring device. Okay. Now, we sort of make this distinction because we'll see that if I had an infinite bandwidth measuring device, I would actually measure infinite noise. But we don't, right? So because we have a certain bandwidth. Okay, so that means if I take that as a bandwidth, then I take this as the mean square. Yeah. Because I really don't know the individual points, right? But this is also the average energy maximum. Again, Boltzmann says, okay, it's not the energy for individual electrons, right? It's the average energy for a lot of the electrons. So we sort of can work with this and say, huh, I can now estimate, or I can have a nice model for the mean square noise of a resistor. Again, this resistor, this is just a way we get to extract that. Okay. And that's equal to 4 KTR times the bandwidth. Okay, so you just mess around with this, right? So it's 4 KTR times the bandwidth. It's actually a good model for the mean square noise of our resistor. Again, this is the variance, right? And we're talking about. It's not a way to predict the actual value of noise. This just gives you an idea of how much energy I have in that particular uh, resistor, the noise energy I have in that particular resistor. Yeah. Okay, so any questions there? So this is actually how we write out uh, the noise in a resistor, the noise power due to thermal noise. Right? And I know that, if you haven't seen this before, this might be a bit you know confusing still, because we are talking about power uh, and a few things here, right? So this looks like a variance. So one of the things that we'll see for noise, it has to have zero mean. This a variance, and noise actually has zero mean. That means if I take a voltmeter just to try and see what the DC value is, it's going to be zero, right? And that's sort of expected, right? Because what happens if you don't have zero mean? If you have noise and you don't have zero mean, then what happens? You can actually extract DC from noise. And if you can extract DC, then you can extract power from noise. Right? And if you can extract power from noise, you will have an infinite source of energy, and then you will be a billionaire yesterday. Right? So that's hopefully we understand that. Okay, you can't really have the non-zero mean, because that means there is DC energy that you can exploit. Okay? And we'll talk about that in a bit, right? But hopefully any questions here. So thermal noise, the way we think about thermal noise now is dependent on several things. Obviously, it's dependent on Boltzmann's constant, and it's called thermal noise because it is proportional to temperature. That means the noise increases, the noise power increases as I increase temperature. And that's the reason why a lot of when you're dealing with uh, very, very high precision stuff like quantum computing, and you want to get very, very good data in and out with very little noise, then that's the reason why a lot of quantum computing stuff is done at near cryogenic temperatures. Because obviously your amplifiers that amplify all those signals have to have extremely, extremely low noise powers. Right? And you operate them now at something as close as you can to absolute zero. Uh, the other things that you can see is that in some cases you do want to cool certain things to get very, very high resolution and so on. But this is a very obviously important property because it's thermal noise. It's going to be dependent on temperature. The other thing, as you can see, the voltage noise, it's dependent on the actual resistance value. So if I were to have uh, two resistors, the voltage noise power of the larger resistor, okay, will be larger. Yeah. So that also plays into, okay, do I choose a high resistance or a low resistance? It actually, we'll talk about that. Depends on the stuff that you need. Yeah. And it depends on this thing. We call this the measurement bandwidth. Right? Uh, and then this gets us to this very interesting, uh, before we talk about the bandwidth, it gets us to a very interesting idea that if it's dependent on bandwidth, can I actually write out the spectrum for noise? Right? Can I plot this with respect to frequency? And it turns out for resistors, for thermal noise, you can, because now if I plot it out, okay, I look at over frequency, how will this look like? Uh, if I do this, then notice that the incremental or the power per bandwidth is actually going to be constant, right? So that means the power per bandwidth is going to be 4 kTr. And, you know, if I have a certain bandwidth B, that is the noise power that I get, right? So that means I can actually write out uh, my what we call noise spectral density. Okay? It means that, okay, I can think of this as some, noise that is actually spread out over frequency, right? And the higher the bandwidth of my measuring tool, let's say, okay, I have, this bandwidth, the more noise I measure. Okay? So this is, if this were, this is something that we see all the time, the spectral noise spectral density of thermal noise is what we call white. Okay? It's called white because it's spread out over all frequencies. And sometimes it's called white, it is actually called white noise. When you say white noise, the spectrum contains all frequencies evenly. Right? So this gives us, again, another, let's look at this from, you know, intuitively, if I want to measure the noise voltage instantaneously, and that means, okay, I put an oscilloscope over here and measure the noise. Even if I measure the noise now, if I know the value of the noise now, it does not help me figure out what the value of the noise is later on at any point in time because the spectral density is white. That means all frequencies are possible. That means, okay, if I measure it a millisecond from now, I won't have any clue. If I measure it an hour from now, if I measure it a second from now, given I actually measured the value of the noise now, it's not going to help, right? Because it's a jumble of every single frequency, right? So the noise power at 1 hertz is just as likely to happen as the noise power in 100 gigahertz, right? So that makes it truly random. But we'll see later on, because we have this particular spectrum, it turns out, A, we can filter noise. right? Just like any other signal with a frequency spectrum, I can filter this. I can move noise from one frequency to the other, like what we do in sigma delta type converters or sigma delta circuits. Or I can actually start, you know, creating noise that is not white, noise that has more energy in some frequency component compared to others. Like we'll talk about that flicker noise and so on, right? But yeah, so these are characteristics of the noise, and this is how we normally try to look at noise, right? What's the spectral density? So I normally would like to plot power versus frequency. Now, in some books, this actually has uh, the term over delta F, right? Because in some books, this is cumbersome, this B. So the reason why I'll explain is that it turns out that it does not have to start from zero. I can take any bandwidth here and get the noise over a certain delta F, right? So for thermal noise. So some books would write out Vn squared equals 4 kTr delta F, right? Just make sure that delta F is sort of the bandwidth of what you're talking about. And hence, the spectral response is normally can also be written as Vn squared over delta F, which is equal to 4 kTr. Uh, so either of these notations sort of uh, say exactly the same thing, right? So either you look at uh, you know the spectral density, how the noise behaves over an incremental frequency delta F, right? Or over a certain bandwidth, but they sort of yeah, they can be the same. This thing actually has a special name. This thing, okay, is sometimes known as spot noise. Okay? That means, okay, if I find a spot here, that's actually equal to 4 kTr. That is the uh, noise over an infinitesimal delta F. Okay? Uh, but the total noise power, okay, is the area under this curve, right? So for example, if I have a bandwidth B here, the total noise power, as you can see, is 4 kTb. Okay. This is just the noise spectral density. So let's be clear. This is in volt squared. Okay. The units of Vn squared is volt squared. The units of spot noise is volt squared per hertz. Yeah. So to get total power, you multiply that with the bandwidth. And this is, we know that this is true, right? Because we know from our systems class, yeah, I can take the power either in time, right? Or I can take the power in frequency, and they're going to be the same. Parsifal's theorem, right? Okay, so any questions here? Again, make sure, let's try to absorb this. This is oh, the good news is that we can simulate this, right? Our simulator and our models actually can allow you to simulate this and look at spectral density and all of that. Yeah, so any questions here? Okay, so once we sort of uh, have this, and you know, what are the other properties of the noise here, right? that I sort of want to look at? Well, first of all, uh, so just as a recap, we want, noise is really expressed as either noise power or spectral density. And I can plot this using this. Right? Now, some books won't have the noise spectral density, but they will actually have what we call the root noise spectral density. Okay? And it's just the square root of that. That means, okay, I plot the square root of Vn squared over delta F. But this actually has very weird units. The units of this is volts per root hertz. Some people like this because you're talking about volts, but it's not really a convenient way because you have this weird units, the square root of hertz. Yeah. But yeah, so people can do this, right? So when you run simulations, you can either specify, I want the noise spectral density, I want the root spectral density. ngSpice or Spectre will plot it accordingly. Okay. Okay, good. So any questions? So we're just starting to characterize noise, right? So, okay, how do we think of noise? It turns out I can think of noise power. I can think of it as a variance of the noise, and it has a frequency response. It depends on how much frequency components I have, and it depends on the value of the resistance, and depends on temperature. Okay. Okay, so a few other things is what happens when so we sort of talked about this, right? The question is, can I actually get power from noise? So we saw that, okay, I get uh, this noise generator. Uh, he said we can't get power, but what if I just put a resistor here, right? So this is my noisy resistor, and I model it as a noiseless resistor with some noise generator. Okay? But if I phrase it this way and we just calculated that, won't I get some power into the resistor? And if I get power into the resistor, can't I just use that power, right? To do some work or to store that power in a battery or a capacitor or whatever. And that's not possible. Why? Because you cannot build a noiseless resistor. So that means this resistor would also have its own noise generator, right? And then you'll see that whatever power I transfer to this resistor's noise is transferring that power right back. So it's not that there's no power being transferred, but because of the noise in the other resistor, you can't really do that. Yeah. But again, you sort of say, but we can measure noise, right? So this is just another thing. We just said that if I connect the noise to an oscilloscope, or actually, since what we're getting is a mean square, if I take the square root of Vn squared, that's actually your root mean square, right? There's a non-zero RMS that I can measure. And it turns out that, okay, if I have a resistor and I have a voltmeter or whatever, right? So a DVM, right, that you have in the lab, or it could be digital or whatever, right? That thing is going to, if it's an old style milliampere movement, that thing is going to deflect because it actually measures, okay, the RMS voltage of the noise. But then you have to ask, okay, that sort of means this does some work again, right? So if you have a meter, the meter deflects, right? You have a meter and it has a needle, and then if you put in that, uh, you know, you try to measure the noise of a resistor, then that actually will deflect, right? But when that deflects, that means that's power. Didn't I just harvest power from the noise? Right? That's an interesting concept. But what do you think? Can I actually use that thought? Can I actually, I don't know, is it a closed system, or what else is going on? It turns out that, yeah, the key here is to try to understand. It's really, if this actually draws some power, it actually has enough power to do work. Why can't I do that for, to harvest stuff? So if the noise here, that's the noise, uh, how do I account for the fact that I'm actually getting some power from the resistor? Okay? So what happens really is that I actually get some power. It goes to my meter. What happens is that resistor actually cools down by a small amount. It loses a certain amount of energy. It loses power, right? Just because I got it from that was enough to move my uh, meter. But it turns out that, yeah, that temperature drops by a bit. But because it's not a closed system, right? Because it's exposed to the environment, that thing, thermal energy replenishes up again. Yeah. But again, this is something that we'll see. This thing, the your milliampere movement also has a resistance, and it also generates noise. And some of the noise is actually sent back into the resistor, right? So you do get, just make sure we understand, we're not breaking the laws of thermodynamics. Um, you will be able to measure it, and it will move that, but it actually it requires there's some temperature change going on, even if it's very small. And not that it can't really power much, right? Because it's not going to be anything you measure with that movement. It's just going to be sent back again, right? So you can't really store stuff. It's really just balancing out how much power I'm getting versus the power I'm actually sending back to the resistor, plus the temperature change. Eh, Okay, so it's, I'm actually oversimplifying a lot of things, but bottom line is that, yeah, you will see that it will change your meter value reading. You can measure it with an oscilloscope, but you can't really, keep the power you got. Right? Okay, good. So any questions here? Now, the second thing is very important. Um, if you can do this for voltage, then since noise is small signal, we're assuming that noise is small by design, then I can actually analyze this. Okay, if I have, you know, some noise voltage with a resistor, okay, an R, I can get the Norton equivalent of this, okay, or, the way books write it is that this is your conductance G, it's 1 over R. And the way we write noise current is this way, right? Just to indicate that it is a noise current. the direction is not significant because we don't really know the actual instantaneous uh, value of the current. It could be going up, could be going down. And I can just have the mean square current. And you'll see if you do the same exact analysis, it's going to be 4 kT G delta F. Okay? Or it's going to be 4 kT delta F over R. Okay? And that is valid as well. So it turns out it's perfectly fine if I can work with voltages or work with currents. This sort of thing, I can do the transformation. Now, a few other things, if I have, you know, resistors in R1 and R2 in series, uh, let's just make a few things clear. If I had, let's say, the noise source of Vn1 squared with noise source Vn2 squared, remember, you cannot add RMS. Right? So when you add, you either add instantaneous voltages, okay? But we can't get instantaneous voltages, so what we add are power, okay? Because we know, hopefully we understand, we cannot add RMS, okay? Because we don't have any phase information for RMS, right? So if I have a two sinusoids and I'm just given, okay, 100 volts RMS, 200 volts RMS, I can't really add because I don't know what the phase is, right? If the phase is 180 degrees, then they subtract. If the phase is 0 degrees, then they just add, right? So normally when we talk about noise, we add powers, right? So if I have two resistors in series, then uh, the total noise is just the sum of the noise powers, right? Because powers add. And this is going to be 4 kT R1 delta F plus 4 kT R2 delta F. And as you would expect, is 4 kT R1 plus R2 delta F. Right. So I can actually have, okay, this is equivalent to some resistor R1 plus R2 and a noise generator of uh, 4 kT R1 plus R2 delta F. Okay. So you can actually add resistors, and it's not going to be a hard leap if I have resistors in parallel, R1, R2. I can use the current equivalent, and then we'll see that, okay, the current is just G1 plus G2 or 1 over the parallel combination or of R1 and R2. Right? You can just use the current formulation to get resistors in parallel. So it turns out that if you have a resistive circuit, I can just simplify whatever resistor circuit and I get the equivalent resistance. Okay? And the equivalent noise generator is just for the equivalent resistance. Vn squared is 4 kT R equivalent delta F. Yeah, let's say delta F. Right. So I can, for a resistor network, I can just look at the two terminals that I'm interested in and get the equivalent resistance, and that's the noise, the equivalent noise generator I get at those two terminals. Okay. Okay, good. So any questions here? We sort of will have a bunch of other examples, but I think, let's just try and start up with trying to understand. Okay, very simple resistor thermal noise, and we know that it has power, and we can characterize it with the mean equal to 0 and the variance equal to 4 kT R delta F, and it also is white. Again, very important, its spectral response is white because there are other noise sources that do not have a white spectrum. Okay, so any questions here? Now, lastly, before we sort of end, I just want to point out a few things. So one, it's really before we go to all the noise analysis, uh, because we talked about resistors, what about capacitors and inductors? Um, they do not generate noise. Okay? So when we say thermal noise, uh, only in devices that dissipate energy. Okay? Like resistors, diodes, transistors, anything that has some resistance actually will generate thermal noise. But inductors and capacitors, the ideal inductor and capacitor, they have therm zero energy dissipation. They have zero loss. Okay? So when we say ideal, so for example, ideal, that means zero loss. Obviously, real capacitors and real inductors would have a certain amount of loss. And if that loss mechanism is resistive, then they will have thermal noise. But ideally, they don't have thermal noise. Ideal devices do not have thermal noise. And why would you think that, you know, just right off the bat, why can't, let's say, a capacitor, an ideal capacitor, have thermal noise? Because this is a key, right? If this actually generated noise, right? And then if I connect it to another capacitor, right, and it's also generating noise, then the problem is you start accumulating power, right? You start accumulating energy with zero ways to dissipate, right? So that means as soon as this generates noise, it generates energy, it starts to charge up the cap, right? And since it does not have any resistance, it's continuously charging up that cap. So again, you violate thermodynamics because now it seems I have an infinite source of energy because these are caps, right? So what happens is, okay, as soon as I get energy, it gets stored. Hopefully we remember energy in a cap is CV squared, or the stored energy is 1/2 CV squared. So if I start storing energy, I store it as charge, I store it as voltage, and if I had noise and it had nowhere to go, no dissipative element, this voltage would just go up indefinitely, right? And it leaves me with this immense, infinite source of energy, which you don't have. And the same thing is true for inductors, right? So the the ideal case, you do not have any noise in capacitors, inductors, but however, oops, we'll talk about that next time. Uh, capacitors, inductors can shape the spectrum of the noise. Okay? That means I can use capacitors, inductors to filter noise. Okay? I can actually, one of the reasons why we'll see when we design amplifiers or, like low noise amplifiers, LNAs in communication circuits, we actually want to start to limit your bandwidth, right? That means, okay, I don't want a lot of excess bandwidth. If I only need 2.4 gigahertz maximum, I want 2.4 gigahertz maximum. I don't want to say, oh, okay, I'll put in some margin. Maybe I'll put in some like 3 megahertz or 3 gigahertz or whatever. That's a bad idea because that means, as you can see here, I have, if I overspec, right, if this is the only bandwidth that I need, I overspec, I actually get more noise. Right? So it turns out I can filter noise by limiting the bandwidth of my amplifiers uh, to make it easy later on, right? So a lot of the amplifiers that we'll look at, the real amplifiers have noise specifications. And if you have noise specifications, then you know the more stringent the noise specification, the harder it becomes. And limiting the bandwidth is one of the easiest way you can do that. Okay? And we'll talk about this when we get to some of the amplifiers. But hopefully, at least today, we sort of got a good intro on noise, at least thermal noise, where it's coming from, and what are some of the characteristics of thermal noise. Okay? So next time, we'll try to schedule when we can do the makeup class. But if it's not next this week, then we'll do it next week. We actually want to look at other devices. Right? What are the noise in diodes? Okay. And what are the noise in MOSFETs? BJT. Okay. Now, we also, one of the keys after we understand this, we'll have a few exercises on this. We want to do what's known as noise analysis. Okay? I'm not really interested in the noise of a single transistor. I want the noise of, for example, an amplifier. Okay? And then sort of start defining what we mean by signal to noise ratio. And we'll look at stuff like, okay, what's the minimum detectable signal based on noise, and so on and so forth. So we'll see that noise actually limits us quite a bit, and we spend a lot of power trying to reduce noise, right? So that's one of the main uh, sources or main, components that eat up power, aside from functionality, right? It turns out when you do a lot of these things, functionality is the easiest thing to achieve. If I want an amplifier with a gain of 100, that's probably very easy. However, if I add other specs like noise, settling time, bandwidth, and so on, a lot of the non-idealities, so that's where I actually put in a lot more power on top of functional power. And that's what we sort of want to minimize. Right? So to be able to do that, we want to sort of understand what's going on. Okay, good. Any questions here? Okay, so since it's almost time, so it will end here. What we'll do is I'll post this, the recording, and then I'll post the slides, catch up on the slides, and then let's post our next homework to get a nice intro to noise. And what we'll do next time is just continue this until noise analysis and to get a bit more understanding of how it affects amplifiers and so on and so forth. And then we can actually start doing a lot more of the, quote unquote, real world amplifier design. Okay, good. So any questions here? Okay, so if there are no questions, we'll end here. Just watch out for announcements on our webpage. And if there are no announcements, we'll just meet again on Tuesday. But we'll try to get one more meeting, even if it's just a recorded thing, or we'll try to set a schedule next week. Okay, good. So if there are no questions, then thanks everyone. Have a great rest of the day and see you guys next time. Okay, bye everyone.